Welcome to Organic Chemistry. Today we are going to explore addition reactions in conjugated dienes. Imagine walking down a long hallway with two sets of heavy double doors separated by just a few feet. If you push hard through the first set, your momentum might carry you all the way through the second set as well. In organic chemistry, a conjugated diene behaves very much like this connected hallway, leading to some incredibly fascinating chemical behavior. Now that we have our hallway analogy, let us look at the chemistry. A conjugated diene is simply a chain of carbon atoms where double and single bonds alternate perfectly. Because these double bonds are so close together, they do not act independently. Instead, they communicate and share their electrons. When an electron-loving molecule, called an electrophile, attacks this electron-rich system, it adds to the molecule and creates a carbocation. Specifically, it forms an allylic carbocation, meaning the missing electron and resulting positive charge sit right next door to a double bond. This brings us to the first step of the reaction. Here we see the chemical formula for the initial attack. The hydrogen ion, which acts as our electrophile, attacks the first carbon atom of our starting diene, 1,3-butadiene. When the hydrogen attaches to the end of the chain, it leaves the second carbon atom short of an electron. This creates the allylic carbocation. The positive sign on the second carbon indicates exactly where the molecule is now vulnerable to the next attack. If the concentration of hydrogen ions increases, this first step happens much more rapidly. Because that positive charge is right next to a double bond, something special happens: resonance. This formula shows resonance in action. The double-headed arrow tells us these are not two different molecules, but two ways of drawing the exact same molecule. The double bond shifts to the middle, which forces the positive charge to move from the second carbon atom to the fourth carbon atom. The molecule shares the burden of the positive charge, creating two different targets for the incoming negative ion to attack. This delocalization of charge is what makes conjugated systems so uniquely stable and reactive. With two reactive sites available, which product actually forms? The answer depends entirely on the temperature. At very low temperatures, the reaction is under kinetic control. This means it takes the easiest, fastest path available, resulting in the 1,2 addition product. However, at high temperatures, the reaction is under thermodynamic control. The heat provides enough energy for the reaction to reverse and try again until it finds the most stable possible resting state, which is the 1,4 addition product. Let us visualize this temperature dependence with an energy diagram. The starting point in the middle is our allylic carbocation. The smaller blue hill represents the fast, easy path to the kinetic product. Because the hill is small, this happens even when it is freezing cold. The taller red hill represents the harder path to the thermodynamic product. This path requires the extra heat of a warm room to climb over that high barrier. But as you can see on the far right, it rewards the molecule with a much deeper, more stable resting place at the bottom. Before we move on, let us see this with a concrete example. We need to predict the major product when 1,3-butadiene reacts with hydrogen bromide at -80 degrees Celsius. The key clue here is the temperature. -80 degrees is very cold, meaning the reaction is under kinetic control. We must look for the fastest possible product. First, the hydrogen adds to the first carbon, breaking the double bond and leaving a positive charge on the second carbon, while the bromide ion floats nearby. Because the temperature is so low, the bromide ion takes the path of least resistance. It immediately attacks the positive charge on the second carbon atom, right next to where the hydrogen just landed. It does not wait for the molecule to undergo resonance. This gives us our final answer: 3-bromo, 1-butene. This is the kinetic product, forming fastest because the bromide ion is physically closer to carbon-2 right after the initial attack, making it an easy target in a cold environment. Now, let us look at a second example, this time at a high temperature. We are reacting 1,3-butadiene with bromine gas at 40 degrees Celsius. Once again, temperature is the most important clue. 40 degrees provides plenty of heat energy, placing the reaction under thermodynamic control. We need the most stable final state. The reaction begins when one bromine atom attaches to the first carbon, creating our familiar allylic carbocation on the second carbon, leaving a second bromide ion ready to attack. Because there is plenty of heat energy available in this system, the molecule has the time and energy to explore its resonance structures. The double bond shifts to the center of the molecule. This movement forces the positive charge to migrate all the way to the fourth carbon atom at the far end of the chain. This internal double bond is highly substituted, which according to Zaitsev's rule makes it a much more stable arrangement for the molecule. Finally, the leftover bromide ion attacks that positive charge on the fourth carbon atom. This locks the double bond into the center of the molecule. This gives us our final result, 1,4-dibromo-2-butene. This is the thermodynamic product. Even though it took more energy and time to form, the high temperature provided that necessary energy, allowing the molecule to settle into its most stable, relaxed state. You might be wondering why this matters outside the laboratory. Understanding how conjugated dienes react is incredibly important in the real world, particularly in manufacturing synthetic rubber for car tires. Chemical engineers use massive chains of conjugated dienes. By carefully controlling the temperature of the reaction vats, they can force the molecules to link up using either 1,2 addition or 1,4 addition. The kinetic 1,2 addition makes the rubber hard and rigid, while the thermodynamic 1,4 addition makes it soft and bouncy. Let us review the key takeaways from today's lesson. Conjugated dienes are special because their alternating double bonds allow them to share a positive charge across multiple carbon atoms through resonance. This shared charge creates two different targets for a chemical attack. By simply changing the temperature, we act as a traffic cop. We can direct the reaction to form either the fastest product at low temperatures, known as kinetic control, or the most stable product at high temperatures, known as thermodynamic control. Great job following along with these advanced concepts.